All right, assignment 3.3. I've actually prepped this a little where I've drawn the graph and so on. So if you need to press pause and do what I did and then press play so we can do it together, that's what you need to do. So for the first 11 questions, I've already kind of set it up. So you would be wise to press pause, set it up with what was given, and then how am I going to draw the derivative. So in number one, I have a slanted line. The slope is 3. Derivative means slope. So all you have to do is draw a line to show the slope is always 3. I'm going to do that in a different color. I'm going to pick purple. And there's the graph of the derivative. Number two, what do I notice? So whenever we have a line, I think of it as directly as slope. When something's curved, then I think of it, maybe a number line would be more helpful. So we have a turning point at positive 1, right? That's at positive 1. Should I have it here? Yes. And this graph decreases, and then it increases around 1. So at 1, the derivative is 0. Before 1, and then after 1, it's negative and then positive. It can be that simple. Number 3. In number 3, I have a horizontal line. The slope of a horizontal line is 0, so the derivative just shows that. The slope is 0. Done. Again, it's wise to press pause and to set it up first. So again, press pause. Here, we'll go through it. I'm going to do a little number line here to make it a little bit helpful. So at 0, it's undefined. And here, we have a positive and then a negative. Now, what's positive in terms of increasing? It's consistently positive 1. So find positive 1, and it's going to be horizontal. So constantly it's 1. And then here, the derivative is undefined, so I put a hole down. And then after 0, it's now negative 1. So again, it'll be a hole, and then it's constantly negative 1 here. So what's the slope? It's 1. What's the slope? It's negative 1. What's happening at 0? It's undefined. There it is. Number 5. For number 5, you're given the derivative, and can you work backwards? That's called the antiderivative, when you work backwards to find what the function would look like. So I'm going to draw a number line to understand both concavity and the derivative. So for the derivative, it has an x-intercept. Where's the derivative 0? At 0, and then it's above and then below. For the second derivative, I'm looking for any turning points. We don't have any. And then I'm looking for increasing and decreasing. So this derivative is only decreasing. So that means this graph is concave down. So at 0 is going to be a maximum. So 0, 0, our starting point, is a maximum, and it's concave down. So let me make sure I stick to my purple. There it is. Number 6. I'm going to draw a number line. For the first derivative, what am I looking for? So where is the derivative 0? So for number 6, that's at negative 1 and positive 1. That's that. Negative 1 and positive 1. And then I'm looking for above and below. So it's below, and then above, and then below. So our function has a minimum at negative 1 and a maximum at positive 1. The second derivative, I'm looking for the turning point. So we have a turning point at 0. It increases, and then it decreases. So this tells me concavity, concave up, and concave down. We have a starting point at 1, 2. Do that in purple. At 1, 2 is a maximum. At negative 1, we have a minimum. Now, I don't have any information where that minimum is, so anywhere below that one works. And then at 0, we have a point of inflection. And so we know it's concave up. So this is decreasing to -1. So decreasing and concave up. And then after 0, it's concave down. It continues to increase and then creates a maximum here. And there it is. So it's concave up, concave down. See how it matches? And at 0 is a point of inflection. It decreases to -1. It increases to +1. And then it decreases. And we have our maximum minimum. Like putting together a puzzle. Number 7. Again, press pause and set it up for yourself. I'm going to draw 2 number lines, one for the derivative and one for the second derivative, and then I'm going to take this information and draw the function. So we have an x-intercept where the derivative is 0 at -1 and +1. I know that it's increasing and then decreasing. So it increases, it's below, that's decreasing. It's above, and then below. There we go. So that means we have a minimum at -1, and we have a maximum at +1. The second derivative, I'm looking for a turning point or where it's undefined. That's 0, and it's increasing and then decreasing. So concave up and then concave down. They give me a starting point. Is there a starting point for 7? I didn't write it down. It's at -1. I forgot to write it down. At -1, 2. So I'm going to find -1 and 2. -1 is a minimum. So this point that I put down is a minimum for the sketch. I know at +1 is a maximum, so I better put that one just a little higher, right? And at 0 is a point of inflection. So I'll put that one in the middle, and now I'm going to connect it. So it is concave up. So it decreases concave up, and it stays concave up to the point of inflection. So it decreases, creates a minimum, and then we stop. Now it's concave down, and it goes through a maximum. And there's your graph. Number 8. I'm going to draw 2 number lines. So how do I look? What do I look for here? So there are endpoints here. So I'm going to make sure they're ends. So really just 0 in the middle. It goes below, and then it's above. For the second derivative, I'm looking for the turning points. So at -1 and +1. And I'm looking for decreasing, then increasing, and then decreasing. This tells me concavity, and this tells me increasing and decreasing. At 0 is a minimum, and these are points of inflection. All right, our starting point, again, I didn't write down, is at 0, 0. So 0, 0 is a minimum. At -1 and at +1, and is it at 2? So it ends at 2 and -2. So I need some points here, and then I connect it with curves. So I know it's decreasing and I know it's increasing. I know at -1 and +1 are point of inflection, so they need to be in the middle. -2 and +2 are ends. And now I'm just going to connect it. So it's concave down, then concave up, and then concave down. And it creates a minimum there in the middle. That's it. Number 9. Again, press pause if you need to. This is connecting 3 of them. So we're going to draw a number line for the function and for the second derivative. So if I look at the second derivative and draw a number line for it, it's undefined at 0, but both sides are above. Now the slope here on the left is 0, and the slope here is +1, and both are above. So when I look at the second derivative, we're going to draw 0 for the slope. And then when we get here to 0, it's a hole because it's undefined. And then after 0, it's going to be positive 1. And so we showed the slope is positive 1, and we showed the slope is 0. Now, I'm also going to draw a number line for the first derivative. And then for the first derivative, again, I'm just looking for above and below and with so on. So it's undefined at 0, and that both are above. And in fact, if I look here in terms of increasing or decreasing, this one here is neither, right? It's not increasing or in terms of it. So when I think of the second derivative, it's really just a slope of 0 rather than increasing or decreasing. The first derivative, definitely both are above for both. So the whole function is increasing. So we don't have a starting point for number 9. So you create a starting point. So if the whole thing is increasing, I'll put 0 right here. And so what do we know? There is no concavity. So that means it's a line. And then after that, it's concave up. And there you go. And so we have a line, and then a curve, concave up, and no concavity, concave up, and the whole thing is increasing. So it matches the number lines. Number 10, I need you to set it up and have an open mind, and we'll work together. Press pause, and now press play. So we're going to draw a number line for the second derivative. So I'm looking for the turning points. So at negative 4 and at positive 4 are turning points. It increases, then it decreases. Oh, we also have a turning point at 0. Sorry. So it increases and then it decreases, it increases, and then it decreases. And so all of those turning points are x-intercepts. It's where the derivative is 0. So at negative 4, at 0, and at positive 4, the derivative is 0. And then it's below, above, and so on. But for this one, it's above, and then below, and so on. We don't, in terms of concavity changes and so on, we can see that the concavity of that derivative changes at like negative 2 or so. So around negative 2 would be a turning point. So like where does the concavity change? So somewhere around negative 2. So at negative 2, we'll create a turning point here. So it's above. The concavity also changes like above around positive 2. So it goes above and then below and then above and then below. And again, these turning points is the point of inflection of the first derivative. So that's the second derivative. Now, what would the graph look like over here? So let's do a first derivative number line. And for this one, I'm looking for where the derivative is 0. So at negative 6, at 0, and at positive 6. And then above and below. So it's below, and then above. It stays above, and then below. So this tells me increasing and decreasing. It tells me there's a minimum at negative 6 and a maximum at positive 6. So let's put down the key numbers I need to put down, including negative 4 and 4. So I'm going to count 1, 2, 3, 4, 5, 6, and 4, and 0. 1, 2, 3, 4, 5, 6, negative 6, and negative 4. What we know is there's a minimum at negative 6. So at negative 6 will be a low point, and at positive 6 will be a high point. We know there's points of inflection at negative 4, 0, and 4. So this is going to, between -4 and, -6 and 6, it's increasing. So we need to just continually have points that are increasing as you go along. So all that matters is that it's increasing, then we connect it with a curve. So this is going to go decreasing and concave up. It goes concave up to 4. So here we go, connecting that. And then between -4 and 0, it's concave down. Between 0 and 4, it's concave up. Between 4 and on, it's concave down with the turning point. And there's your graph. So the concavity, the turning points, it's decreasing, increasing, decreasing. It matches going across. Number 11. Can you please set this up, press pause, and then press play. So for the second derivative, we have a turning point, or really where the derivative is undefined. Here at the corner at 0, it decreases and then increases. So it's concave down and then concave up. For the second derivative, what that would look like is at 0 would be a hole. And then it's going to be above and then below. Or below and then above. We could also draw it curved in a different way. But it's important to know it's below and then above, and then at 0, it's undefined because of the corner. For the function, or for the first derivative, to get to the function, we do have an x-intercept. It's 0. It's really undefined, but it's 0 there. It's not undefined for the derivative. There's a point there. So 0 is that turning point. It decreases. Both sides are above. So that means this entire function is increasing, and 0 is an important point. So I'm going to put 0 right here. It's an important point. You can put it anywhere. This whole thing is increasing. So first it's concave down, and then it's concave up. All right, enough of that, right? I hope that was helpful. You can go back and do them again, and then once you start getting stronger. Number 12. I don't know how much graphing's left here. Let's see. Oh, more graphing. I love graphing. Like trigonometry. Find the vertical asymptotes and behavior, relative extreme, and then graph it. So we have a function, 1 over x squared minus 2x subtract 8. A great first step is to first factor it. So we factored the denominator. If I was asked for where the vertical asymptotes are, that's the denominator. That's 4 and -2. The end behavior is the horizontal asymptote. Because the denominator is more powerful, the ends are going to 0. What else? Oh, the extreme points. We do need to find the derivative. So the bottom times the derivative of the top, that's nice, minus the top times the derivative of the bottom, and then the bottom squared. I'm just going to do this. So times 0, that's simple. -2x, and then a negative times a negative is +2. Just look at the numerator. Make the numerator equal to 0. Solve it. Add 2x if you need to, but it's +1. So at +1 is a critical number. We're going to draw a number line for that and see what's happening at +1. We also need the domain restrictions, which are 4 and -2. So those are my intervals. So if I plug in a number smaller than -2 into here, the bottom's always positive. So if I plug in negative whatever, a negative times a negative, this will be positive. If I plug in 0, it will be positive. If I plug in 2, it's going to be negative. And if I plug in a number bigger than 4, it's going to be negative. And so that means we have a maximum at 1. And so it increases and then decreases with the maximum at 1. So we have a relative max at 1. How do I find the y-coordinate? Is I plug it into here. So 1 take away 10, negative 9. So at negative 1/9, we have a maximum. And then we draw the picture. So if I want to sketch this, start with the asymptotes, which are at 4 and negative 2. We also have our end behavior at 0. We have no x-intercepts because the numerator is just a number, no variables up there. So we do have a maximum at 1 and negative 1/9, so just barely below here. That's a turning point. And then we have to sketch the rest. So it's going to increase, then decrease, then so on. So in the middle, I can tell you the behavior of it towards the asymptotes. These are odd asymptotes, so that means one end goes down and the other end goes up. And then curve to the end behavior. One end goes down, one end goes up. Curve to the end behavior. So an odd asymptote means that the exponent is an odd number, which means the behavior, one end goes up and the other end goes down, to put the puzzle together. All right, number 13. F at x equals x times x subtract 4 cubed, and we need to find the extreme points of inflection, then graph. And it tells you the second derivative is this. So we're going to take the first derivative, that's the first, times the derivative of the second, plus the second times the derivative of the first, which is 1. To make it easier, I'm going to factor out x subtract 4 squared, and then what I'm left with is 3x plus x minus 4. Then you take each one and make it equal to 0. So for here, one answer is clearly positive 4. If I take this equal to 0, just on the side here, that's 4x minus 4 equal to 0. Then the other answer is positive 1. That makes it 0. Those are our critical numbers. So we're going to put down 1 and 4. This is the derivative line. If I plug into here, 0 would be squared, 0, negative. So a positive times a negative is negative. Between 1 and 4, like 2, that's a positive times a positive. And then any number bigger than 4 would be positive. So we have a minimum at 1, and we have no turning point at 4. For the second derivative, the critical numbers are here, 4 and 2. So if I plug in 0, it's a negative times a negative. Plug in 3, and it's a negative. And again, you can look at the multiplicity too to know the signs are changing. So this tells me concavity. We have point of inflection at 2 and 4. So actually, we need to actually find what these points are. Sorry. So at 1, we have a minimum. So I need to plug 1 into here. So 1 take away 4 is negative 3, and negative 3 cubed is negative 27. So at 1 and negative 27. Then we have points of inflection at 2 and 4. So again, to find the y-coordinate, plug it into the function, or the original. So 2 take away 4 is negative 2 cubed, which is negative 8, times 2, which is negative 16. To plug 4 in, the answer is 0, so that's simple. And then draw a sketch of this. So we have 4, 0. We have 2 and negative 16. I'll put that here. And then 1 and negative 27. I'll put that here. And then the concavity. So it's concave up with the turning point. After 2, it's concave down, and then concave up. And also understand the end behavior, x to the fourth. Understand decreasing, increasing, concavity, and there's the sketch of the function. And again, this point here is 2 and negative 16. This is 1 and negative 27, and 4 and 0. And those are the important points on the graph. Number 14. What? No graphing in 14. Sad. So number 14 says use the second derivative test. So we have f at x equals x cubed minus 3x squared minus 5. And we're finding the extreme points. So first I need to find the critical numbers, take the derivative equal to 0, and then solve it. I'm going to factor out 3x. And the two answers are 0 and 2. Those are my critical numbers. Then I need to know the second derivative. So the second derivative would be 6x minus 6. And then I plug 0 into the second derivative. It's negative, which means it's concave down, which means it's a maximum. So then I write down there's a relative maximum. And to find the y-coordinate, you plug it in here and you get negative 5. If I plug into the second derivative 2, that's a positive answer, which means it's concave up, which means it's a minimum. So there's a relative minimum. When x is 2, plug 2 into here. What's that? 8 minus 12, negative 4, negative 9. Just making sure, yeah. And there it is. So that's using the second derivative test to find the turning points, which you did, or the extreme points. Number 15. In number 15, use the following information to sketch a possible graph. So f at 0, f at 4 equals 0, f at 2 equals negative 2. I'm just going to write it down. The derivative, I'm going to do a number line for the first derivative. So it says the derivative is negative when x is less than 2. And the derivative is positive when x is greater than 2. And the derivative doesn't exist here. So it's undefined here. And then do a second derivative. And it says only 0, in that the second derivative is negative, except at 2. Sorry. So the whole thing is negative, but it's undefined there. How can I draw a graph of this? So start with the points that you're given. So 0, 0, 4, 0, and 2 and negative 2. This is going to be concave down throughout. And it decreases and then increases. So it's concave down. It's concave down, and the derivative doesn't exist here because of the corner. So it's concave down, it decreases, it increases, and it matches. Number 16. Find the C value for the mean value theorem. That's when A rock equals I rock. You're given a function, f at x equals x cubed minus 2x plus 3, and you're doing it from 0 to 2. So step 1 is the A rock. So that's f at 2, subtract f at 0 over 2 subtract 0. So if I plug in 2, that's 8, take away 4 plus 3, plug in 0. So if I simplify that, I get 2, just making sure I did it right, looking at my answer key. And then take the derivative, which is 3x squared minus 2, and making it equal to the A rock, which is 2. Add 2, divide by 3. Now, when understand my domain restriction, and so when I square root, I don't have to simplify this, and it's not positive and negative because it's between 0 and 2. So that is the C value right there, the square root of 4/3. Number 17. Find the absolute minimum and maximum of this function from 0 to 4. So to find the absolute minimum and maximum, I'm first going to find critical numbers in that restriction. So to find the critical numbers, take the derivative equal to 0 and solve it. So you would get positive and negative 2, but I only want positive 2 in the interval. Then I do a table of values. I use the critical number and the ends, and then I plug it into here and get my answer. 0 gives me negative 2, positive 2 gives me negative 18, and 4 gives me 14. So the absolute maximum is the largest y value, and the absolute minimum is the smallest y value. So it's 14 and negative 18. Number 18. Without using a calculator, sure, sketch. So my goal is to sketch this. So my first step is to sketch this and then reflect. So how do I do that? It's a parabola. Things I would look at, I would factor out negative x and realize the intercepts are at 0 and negative 6. If you took the derivative, you get negative 2x minus 6, make it equal to 0. If you add 2x and then divide, you can see it's negative 3 is a turning point. I know because it's a negative x squared that it is concave down, and that is a maximum because of concavity. So if I was going to graph f at x, without the bars, this is what it would look like. I'm not going to call that f at x. Anyways, it would be 0 and negative 6. And at negative 3 is a maximum. If I plug negative 3, actually I should do that. So we do have a maximum at negative 3. And then I plug it into here, and you get negative 9 plus 18, so that's 9. So at negative 3 and 9, we have a maximum. And then this is what the graph would look like. So when I graph with the absolute value bars, this part of the graph stays the same, but the part that's below is now reflected up, and this part is reflected up. So that's what it looks like when you put the bars down. So when you have absolute value bars, graph it without the bars, and then reflect, and you have the graph. Number 19. The graph of y equals ax squared plus bx plus c passes through the point 1, 6. So already I know this part. Plug in 1 and 6 and reduce it down. It has a tangent line, so if I take the derivative and I plug in, make it equal to 0, the x value is 16. So I have 32a. Oh, I should just plug in 0, 16 too. So if I plug in 16 and 0, plug in 0 for x, and it's equal to 6, c is equal to 16. So I already have that part. So when you take the derivative, 2ax plus b, if there's a minimum at 0, 16. So that means when I plug in 0, the answer is 0. I was plugging in the wrong value. So that means b is equal to so you take the derivative, 2a, right? You plug in 0. So when you take the derivative equal to 0, at 0 is 1. So I get b is equal to 0. And then a subtract 16 would have to equal negative 10. That's what I got. Let me see. My answer key doesn't seem to see that. So if you have a minimum at 0, 16, you take the derivative equal to 0 and plug in 0. So I get a different answer there. Anyways, if I'm wrong, I'm wrong. This is what I get. Number 20. If the only critical number of a function is 3, and the derivative at 2 is negative 6, and the derivative at 4 is 7, does the function have a minimum or local maximum at 3? So assume it's continuous. So if there's a critical number at 3, and the only critical number is at 3, so before, if you plug in 2, you get a negative. If you plug in 4, you get a positive. That would mean that 3 is a minimum. If it's the only critical number. 21. In 21, 3 is the only critical number again. And it says the second derivative at 3 is negative. Well, that's concave down, so at x equals 3 is a maximum. 22. True or false? A fourth degree polynomial has 3 critical numbers. Seems like that would be a false. Like x to the fourth would only have 1 critical number. That'd be 0. 23. Every fourth degree polynomial has at most 3 critical numbers. Again, that seems like false. Has at most? Oh, the other way. There's no way to have more than that. So if you think of x, that means how many turning points there could be. So that part is true. So at most, a fourth degree poly has 3 critical numbers at most. That's so many. There can't be more than 3 turning points for a fourth degree polynomial. And if you take the derivative all the way down, you could see that in terms of that. It'd be impossible to have 4 critical numbers, 4 answers to it. 24. If a poly has 2 critical numbers, one must be a max and the other must be a relative minimum. So if you have 2 critical numbers, could they both be maximums or both be minimums for number 24? And of course that's false. What's an example where you could do it? And so here's an example where both of these would be minimums in terms of it, for the 2 critical numbers that you get out of it. All right. 26, 25. Oh, these are still true-false questions. We're almost there. The first derivative at 2 is positive, then f is increasing when x equals 2. That's true. That's what it means. 26. If a function is increasing at 2, then the derivative is greater than 0. That's true. That's what it means. (27) The derivative. Make it calculus friendly. You don't have to simplify this. This is the product rule. So that's the first times the derivative of the second with the hook plus the second times the derivative of the first, which is 1. 28. Can you derive implicitly? These are so important to practice, right? Press pause and try it. So the derivative, this is the product rule. The first times the derivative of the second times the derivative of the first. This is 1 with a y prime, and that's 0. Factor out a y prime from negative 2x, and that would be 1 left over. Add 2y and subtract 2x to the other side, and then when you divide, you have the derivative. Last one, 29. Without using a calculator, do everything and graph it. So this is a good place to end. And let's do it together. I really would love for you to try it first. Do everything and graph it. Well, I guess we're not finding the turning points, it says. Just all the pre-calculus work. And then do it. We're going to factor out. Notice x creates a hole. So that's 0. So we have a hole at 0. If I plug 0 in, I get 2 divided by negative 1. So there's a hole at 0, negative 2. X-intercept's at negative 1, and it's odd. There is no y-intercept because there's a hole there. The vertical asymptote, what didn't get removed, that's positive 1. The horizontal asymptote, power term over power term. That's also the end behavior. And then sketch it. So at 0, 2, 0, negative 2, that's a hole. The x-intercept's at negative 1. There's an asymptote at 1. There's a horizontal one at 2. And then sketch what this would look like. And that's it. All right, Mr. G Math over and out. I am proud of you for doing your work, not giving up, doing your best. Until next time.